I hope now you are familiar with singly reinforced section, beam, analysis and design. If not, please read or watch previous videos on singly reinforced section analysis as well as design. In this session, we will discuss about doubly reinforced beam. What is doubly reinforced beam? If the applied moment is greater than the limiting moment of resistance of a singly reinforced section, we can have three choices. The choices are, if possible, increase the dimension of the section, preferably depth. Of course, when you are increasing this depth, you mean to increase the limiting moment carrying capacity of the beam. Next is, the limiting moment carrying capacity of the beam can be increased by adopting higher grade of concrete. The next alternative can be to incorporate steel reinforcement at compression zone in order to increase the moment of resistance of section. So, reinforced concrete beams provided with steel reinforcement on both tensile and compression side are called doubly reinforced beam. While in singly reinforced section, we used to have only tension reinforcement, okay, whereas for doubly reinforced beam, we will have both tension as well as compression reinforcement. Now, this compression reinforcement has been added in order to increase the moment of resistance of the section, such that it can take more applied moment which is expected on beam for certain cases. Now, when to opt for doubly reinforced section? The situations in which the doubly reinforced section to be adopted can be like for architectural or any other construction problem if the depth of reinforced concrete beam is restricted. Like if an architect restricts the depth of the beam to say 450 mm. Now once this depth has been fixed, it means the limiting moment carrying capacity of the beam has been limited. And only way to increase it is to adopt higher grade of concrete. But suppose if you are working with a fixed grade of concrete and fixed depth of the beam, then your limiting moment carrying capacity is going to be fixed. So the obvious choice which you have is to go with a doubly reinforced section. Now next is in some cases bending moment at the section changes the sign due to variation in loading. For example, situation when we have moving load which is acting in a continuous beam, that can also result in change in bending moment sign. By changing bending moment sign, I mean to say that there can be alternate compression and tension in the extreme fibers of the beam. Like suppose if I consider the bottom fiber, at some point of time you may experience tensile stress, and at other instance you may get compressive stress in the bottom fiber. Also, like suppose if you have some precast beams or precast member, so there also during handling it is possible that you can have reversal of bending moment. One more example we can consider, like suppose if we have bracing members in frames. Now due to the change in direction of this lateral load, we can get this change in sign of bending moment. We offer doubly reinforced section also to improve the ductility of beam in earthquake regions. Incorporation of compression reinforcement along with tensile reinforcement increases the stiffness of the beam. Thereby, it reduces the long-term deflection. Well, now we will study the analysis of doubly reinforced section. For this, we will consider a rectangular section at ultimate limit state. Here we have a rectangular section with tension reinforcement as well as compression reinforcement. This compression reinforcement is placed at a distance d dash, that is the distance between the centroid of the compression steel and the extreme compression fiber in the concrete. Okay, we have the section property that is the width of the beam given as B and effective depth D. Now, the distribution of stresses and strain in a doubly reinforced rectangular section are similar to those obtained in a singly reinforced section, except that there is a stress in compression steel. So we'll be having additional stress at this particular level, and that stress will be because of the compression steel. So let us see the strain diagram first. So at ultimate limit state, the extreme top fiber of the concrete which is in compression will reach its ultimate value, while the strain in steel, let us say that it is given by epsilon ft. We'll join this to strain. Here you can see here the strain is becoming 0. So xu is neutral axis depth from the extreme compression fiber. Now at the level of steel, due to compatibility, whatever strain in concrete will be there, same strain is going to be present in steel also. That is, strain in steel will be equal to the strain in concrete which is surrounding the steel. So at this particular level, we have the strain in concrete equal to strain in steel, and this strain can be computed using similar triangle. So this similar triangle, you can see this is a bigger triangle, this is a smaller triangle. So from these two similar triangles, you are going to get an expression for the strain of compression steel, so which is given by 0.0035 into xu minus d dash by xu. Now this section can be split into two sections. One is singly reinforced section with full concrete, where the steel is having area of AST1 plus we have steel AST2 plus ASC. So if I superimpose these two sketches, finally what we are going to get? We are going to get this section. Okay. So firstly what I have done, I have split this doubly reinforced section into two parts. In one part we have concrete with one part of tension steel, and another part we have only compression steel and a part of tension steel. So it means your total tensile steel will be equal to AST1 plus AST2. Now this looks like a singly reinforced section, so we can plot the stress block diagram or stress variation diagram above neutral axis where concrete is in compression. Okay, so we know this resultant compressive stress or resultant compression force in this section is going to act at a distance of 0.42 xu from the extreme compression fiber. Also we have tensile force T1 which is acting at the level of tension steel. Next we'll come to this diagram. Here we have compression steel. So in this compression steel, we'll be having ultimate compression force in the steel which is located in the compression zone. Whereas here the tensile steel is subjected to T2 tensile force because of the ultimate load. Now, if I want to know what is the total compressive force which is acting above neutral axis, it will be sum of what? Sum of CUC, that is for this section, ultimate compressive force for a singly reinforced section, plus CUS, that is the ultimate compression force in compression steel. Okay. What will be CUC? Since the singly reinforced section, it will be average stress 0.36 FCK and this area BX. Now for computing compression force in ultimate steel, here you see the force in concrete area. In this we have considered entire area as concrete, but actually there are certain areas like this. Here this area should not be actually present. Okay, this area actually should not be present. Now this force in concrete area is actually displaced by how much? It is displaced by area of steel in compression. So exactly at this particular level, you'll be having stress in concrete equal to how much? 0.45 FCK. So here, exactly at this level, we can see the stress in concrete is nearly equal to 0.447 FCK. So actually, if this area is not there, we have to subtract that force which is actually acting in this area. Now this area is what? It is equal to area of steel in compression. This will be counted in compressive force in your compression steel. So here we see, if I see this expression, FSC into ASC is your compressive force in compression steel, minus actually this area was made up of concrete which has been replaced by steel. Now this force has been already added in CUC. So that I have to subtract the force which is going to be here. So that force will be how much? So the stress here, it will be 0.45 FCK into ASC. So that I am actually subtracting in the compression force in your compression steel. Okay. Once you get the total compression force, we can compute the tension force. The tension force will be equal to T1 plus T2. Now T1 will be what? So generally what we do, we always try to design an under reinforced or balanced section, and we know when we go for under reinforced or balanced section, the tensile reinforcement yields. So T1 will be how much? Design yield stress into AST1 plus design yield stress into AST2. So that's why here it's been 0.87 Fy AST1 plus 0.87 Fy AST2. So this can be written easily. T equal to what? 0.87 Fy AST. Now in order to compute neutral axis depth, what we do is equate total compression equal to total tension force. If you do C equal to T, you will be able to compute the neutral axis depth. Now for FSC, which is your stress in your compression steel, this value will depend upon what is the strain in your compression steel. Now based upon your strain in compression steel, you will be able to know what will be your value for FSC. Okay. So you remember, for computing neutral axis, we have to equate C and T, and in order to compute neutral axis, so please see, FSC depends upon strain in your compression steel, which depends upon neutral axis. So there has to be some initiation with certain assumption on FSC so that we can compute the neutral axis depth. Next, once we get the value of FSC XU, the ultimate moment of resistance can be computed. Like for this section, it will be what? CUC into lever arm. So CUC into D minus 0.42 XU. Okay, so when you compute neutral axis depth, you will be able to compute MU1. This is moment of resistance of section 1. And if I want to know what is the moment of resistance of this one, so here you can see you have compression force, here you have tension force. How much is the lever arm? It is D minus D dash. If you see the geometry, like from here to here, it is D dash. From this extreme top fiber to this distance, from the centroid of tension steel, this distance is D. So lever arm is D minus D dash. So I can write mu2 equal to what? The compression force in your compression steel into this lever arm, which is D minus D dash. So if I want to know what is ultimate moment of resistance, sum this up, mu1 plus mu2. Okay. Let us consider balanced doubly reinforced section, which will be needed when you design a doubly reinforced section. Now we know over reinforced sections are undesirable, both from the code viewpoint of lack of ductile failure as well as the practical viewpoint of loss of economy. Hence, from a design viewpoint, it is necessary to restrict the depth of neutral axis to the limit prescribed by code, that is XU max. Okay. So again, we have this rectangular section with tension reinforcement as well as compression reinforcement, with tension steel being AST and compression steel being ASC. Now this compression steel is having an effective cover of D dash from the extreme compression fiber. Here B is the width of the beam and D is the effective depth. If we see the strain diagram, we have ultimate strain in the extreme compression fiber of concrete, which is 0.0035, while the strain in steel will reach the yield strain value. So if we join this here at this particular point, your strain is becoming 0. So this is the location of the neutral axis, which is located at a distance of xu max from extreme compression fiber. So this xu max value is also called limiting neutral axis depth or maximum neutral axis depth, and we have seen earlier what and how you can compute this xu max. For standard steel like Fe250, Fe415, Fe500, this value has been given in IS 456-2000. Now once we restrict the neutral axis depth as xu max, we get a balanced doubly reinforced section. Now we would like to find out what is the strain in steel at this particular level, which is epsilon SC, that is strain in your compression steel, which is equal to the strain in concrete at this particular level. So this can be computed with the help of this similar triangle, this bigger triangle and this smaller triangle. So if you do that, we'll get an expression for strain in compression steel, which is related with the limiting neutral axis depth. Now this section can be split into two parts. One will be a singly reinforced section. Now the neutral axis depth is equal to the limiting neutral axis depth. So this AST1 will correspond to limiting tension steel or maximum tension steel. That's why AST1 will be equal to AST max. Okay. Now plus the other part. Now in the other part of tension steel, that is AST2, and this is ASC, that is area of steel in compression. If we superimpose these two sections, it will give me this section. Now here you can see AST is equal to AST1 plus AST2. We already know the value of AST1. This AST1 is equal to limiting tension steel or maximum tension steel, corresponding to a balanced singly reinforced section. If I see this diagram, so from here this compression force will be located at a distance of 0.42 xu max, and here we will be having at compression steel level compressive force of CUS, and a tension force which is going to act at this reinforcement will be T2. So the total compression will be equal to CUC plus CUS, whereas CUC will be average stress 0.36 FCK XU max into this area, which is B into XU max. And if I want to know what is CUS, we'll compute strain in compression steel. Once we compute the strain in compression steel, we can either go to stress strain curve of steel. From there we can get corresponding to this epsilon SC, we can get the value of FSC, or from a table of stress strain value of steel for different strain, we can get the value for FSC. How to compute ultimate moment of resistance? Now for this section, which is a singly reinforced section, balanced at balanced condition, so mu1 will be equal to limiting moment of resistance, while here the ultimate moment of resistance will be, if I consider compression into this lever arm, so it will be CUS into this lever arm is equal to, from geometry, it is D minus D dash. So if you sum this up, we will get mu equal to mu lim plus FSC into ASC into D minus D dash. Now in order to compute ASC, what we can do, we can equate CUS equal to T2. Now from here, what will be CUS? It will be FSC into ASC, and since the steel is yielding, it will be 0.87 Fy AST2. From this expression, if we have applied ultimate moment, which is greater than mu lim, we'll be able to find out area of compression steel. Now if I substitute over here, what we can do, we can compute AST2. So here you can see you will be able to compute total tension steel as well as total compression steel for a doubly reinforced section which is in a balanced condition. The same formula is given in IS 456 in annexure G. So we have annexure G, which is in page number 96. Come to clause number G 1.2. Here you see section with compression reinforcement. It's written where the ultimate movement of resistance of section exceeds limiting value, compression reinforcement may be obtained. So here you see mu minus mu lim equal to FSC into ASC into D minus D dash. Here also you can see mu equal to this. If I bring this mu lim in the left hand side, it becomes mu minus mu lim. So this and this expression, it's same. In order to compute FSC, it's written design stress and compression reinforcement corresponding to a strain 0.0035 XU max minus D dash by XU max. So this is the strain, and the same strain you can find here. Okay. In order to compute AST2, see this expression ASC into FSC divided by 0.87 Fy. This you can see from here, you can find AST2 equal to what? FSC by ASC divided by 0.87 Fy. So basically this balanced doubly reinforced section is going to be helpful for you when you're going to design a doubly reinforced section.